Hello student, welcome back to lecture series on linear differential equation with constant coefficient. This one is the last point from our this chapter, okay, that we are going to continue here in our today's lecture, which is the symmetrical simultaneous differential equation, okay. So already we have learned plenty of the types, okay, so in our channel. So if you interested to see, go and check in my playlist, okay. So in my today's video I'm gonna explain to you all symmetrical simultaneous differential equation and how can we solve or how can we find out the solution for such a differential equation, okay. So now see that behind of every differential equation that we learn, linear differential equation or any other differential equation, okay, so what we do, we try to remove the differentiation or we try to remove integration differentiation from our given result and we simplify into the function, okay. Same we are going to replace here in our symmetrical simultaneous differential equation, okay. Now let me define first of all what is meant by symmetrical simultaneous differential equation, okay. So definition for symmetrical simultaneous differential equation, it says that whenever we have equation of the type, okay, whenever we have equation, let me write here, okay, whenever we have equation of the type, okay, equation of the type, okay, equation of the type, which type of the equation? Dx by p, dy by q and dz by r, okay. So when we have such a equation like instead of that p q r, you will get some another equations here, okay. Equation of the variable in the form of x, in the form of y, or in the form of z, okay. Yes, so whenever we have equation dx by p, dy by q, dz by r, such a type of the equation we consider it as the symmetrical simultaneous differential equation. And in our next point we are going to learn how can we solve this method, how can we solve this symmetrical simultaneous differential equation in order to remove that derivatives, okay, and we get to find out the required function behind of this, okay. Yes, now let me explain here what is the p. Dx by p, it is here now. So if denominator is a p and the numerator it is a differentiation of x, that means p it is also the term of x, okay. So p is term of x, okay, or a function of x. P is a function of x, okay. P is a function of x. Now see that similarly we have q here, okay. So if numerator in the form of a dy, so we consider q is the function of y, okay. That means we cannot say that q is a function of y. We can write x plus y also, okay, as the function for q, okay. Yes, you can write this one. So we have to do some of the adjustment in order to solve this symmetrical differential equation, okay. Yes, q is function, okay, function of y, okay. Q is the function of y, and similarly r is the function of a z, okay. R, okay, is the function of z, okay. R is the function of z here. Now see that this one we consider is the symmetrical simultaneous differential equation, okay. So there are simply or mainly two methods for solving such a equation. The solution of such a system consists to independent relation of the type, okay. So let me write the type here, okay. So we write it's a solution, okay, solution for this differential equation. So you will get the two different solution. You will get the two different solution for solving after solving the symmetrical simultaneous differential equation, okay. And how the solution it look like, as we have the function of x, y, z, you will get the solution in the form of x, y, z itself. So solution f1 of x, y, z, which is equal to first constant, and f2 of x, y, and z, we get the second constant here, okay. Yes, this one is our required solution for our symmetrical simultaneous differential equation, okay. Now pq are in the term of x, y, and z, and these are the two solutions, okay. So now I explained here this one is the solution, but we have to go for some of the adjustment, some differentiation, or need to apply some methods here to land on these two functions, okay, to land on these solutions, okay. So in order to find out these two solutions, we have two different methods, okay. we have two different methods. One, it is a combination of a grouping. Okay, what is the first method? Which is a combination of grouping method. Okay, that we consider here for finding the symmetrical simultaneous differential equation. And the second method, we have methods of a multiplier. Okay, so we have next method, methods of a multiplier. Okay, so we go for finding the solution of symmetrical simultaneous differential equation using method first. Okay, methods of a combination or group. Okay, yes. So here method first, I will explain to you all the method first. Okay, what is method first? Method first is a method of a combination or group. Okay, method of or group. Okay, so we consider this one is a method of a combination or method of group. Okay, yes. So whenever we have equation, now see that we are dealing with the symmetrical simultaneous differential equation. Obviously that equation, it remains same, dx by p plus dy, which is equal to dy by q and dz by r. Okay, this one is the given symmetrical simultaneous differential equation. So we have to solve this equation using method of a combination. Okay, method of combination. We are going to apply this method. Okay, we are going to apply this method in order to solve this symmetrical simultaneous differential equation. Okay, yes. Now method of grouping means, or method of combination means, we have to create a group. We have to create a group. Okay, so how can you create the group? Now see that we can create first with the second with the third, or first with the third. Okay, so we can create the group. How can we create? First with the second, plus we can make a more group, second with the third, or you can make another first with the third here. Okay, yes. Now let me write the group, which how many groups are possible. Okay, possible group. Okay, possible groups. Okay, first possible group, dx by p, which is equal to dy by q. So I made this one is a first as a possible group. Okay, yes. Next, second, you can make a dy by q is equal to dz by r. Okay, dy by q, which is equal to dz by r. Okay, this one is the second. That means first with this one is a group, second with this one is a second group, and what we have third possible, dx by p, which is equal to dz by r. Dx by p, which is equal to dz by r. Okay, so this three grouping, it is here possible for our given method of given symmetrical simultaneous differential equation. Okay, first is a dx by p, second with a dy by q, second dy by q. Okay, dz by r, and last dx by p with the dz by r. Okay, these are the three we have grouping here. Okay, and we have to take that grouping and need to solve by using variable separation form. Okay, we have to solve. How can we solve this one? Now see here carefully how we are going to solve this one. Variable. Okay, variable. We have to solve using variable separable form. Okay, or we call it as the variable separation form. Okay, so we use variable separation form and we solve this simultaneous differential equation. Okay, symmetrical simultaneous differential equation. Now see that this one is our required first method. Okay, and we land here on the our given two solution, f1 of xyz is equal to c1 and f2 of xyz which is equal to c2. We work on these two solution. Okay, yes. So we go for some of the example, then concept will be clear for us. Okay, yes. Let's go for one of the example right now. So see here, I added one example, dx by y square plus dy by x square plus dz by x square y square z square. Okay, now we can see that our function is in the form of, okay, symmetrical differential equation is in the form of dx by p, dy by q, dz by r here. Okay, what is the value for p? Y square. What is the value for q? X square. And what is the value for r? X square, y square, z square. Okay, these are the value for p, q, r. Okay, compare how we are going to compare dx by p, dy by q, and dz by r. Okay, this one is the comparison between two. Okay, and now see that we are going to apply method of combination or grouping method. Okay, so we are going to make the groups. Now see that we can make the group dx by y square, which is equal to x by x dy by x square, first group. Now see that first group I found here, dx by y square, which is equal to dy by x square. It is not that necessary that you have to take the 2 1 first, okay? So you can take first with the third, you can take it second with the third, okay? So you can go for 3 of this form, okay? It is completely up to you. Okay, now see that how I'm going to apply variable separation form, okay? How I'm going to apply variable separation form. Variable separation form, it says that we have to separate the variable as per our given differentiation, okay? And now see that dx, it is here, it's a term, it is here, okay? Dy here, there is a term here. So what we go take that x square here, we take that y square here, okay? Yes, so we write x square dx, which is equal to y square dy, okay? We write x square dx, which is equal to y square dy. Now what we do, we have to remove that dx and dy in order to get the function of f of xyz, which is equal to c1. f1 of xyz, which is equal to c1, means it do not have any differentiation or any integration. These are the simple function, okay? So what we do, we are going to remove that dx and dy from here, okay? So if you want to remove that dx and dy, so what we do, if you want to remove differentiation, we apply simply integration. So simply I take the integration from both sides, okay? So integration of x square dx, which is equal to integration of y square dy, okay? Integration of x square dx, which is equal to integration of y square dy. Now see that integration of x square, x raised to n having integration x raised to n plus 1 upon n plus 1, okay? That means x raised to 2 plus 1 upon 2 plus 1 is the integration for x square. Y square having integration with respect to y raised to 2 plus 1 upon 2 plus 1. As we are taking the integration, so we take it as the some constant, okay? So here we write a constant c1, okay? Because every integration gives us the constant, okay? This one is a normal concept, okay? Yes, so x raised to 2 plus 1 upon 2 plus 1, solve it further, x square by x cube by 3, okay? X cube by 3, x raised to 2 plus 1 upon 2 plus 1, x cube by 3. Take this term here, y cube by 3, which is equal to c1, okay? So we write x cube by 3 plus y cube by 3, which is equal minus y cube by 3, which is equal to c1. Now see that 3, it is a common here, take it outside and take it to the other side, it goes to the multiplicand. So we write x cube minus y cube, which is equal to 3 times c1, okay? And in our differentiation, all constant term behave same. What do constant term? All constant term behave same here in our differentiation. So we write 3c1 as only c1, okay? That means 3c1 and only c1, both are the similar terms here in the differentiation. So we got the first solution, c1, which is equal to x cube minus y cube, okay? This one is, that means we now see that we have solution f1 of xyz, which is equal to c1, okay? Now we can see that here f1 of xyz, which is equal to c1, okay? So this one is f1 of xyz, which is equal to c1, okay? Compare this one, we got the function f1 of xyz, it is here, and constant c1 here, okay? Yes, so as we have symmetrical simultaneous differential equation possesses two different solution, okay? Two different solution means f1 of xyz c1 and f2 of xyz, which is equal to c2, okay? So let's go for finding the another solution. For another solution, we have to take any other comparison, okay? Any comparison you can take it from here, okay? Yes, so what I'm going to do, I'm going to consider dx by y square and dz by last term, that means dx by p and dz by r, okay? So next step I'll write here for the next solution, okay? For the next solution, dx by y square, which is equal to dz by x square, y square and z square, okay? This one is our next step for the solution, okay? Yes, let's go for finding the solution for this one. We apply variable separation form or separable form, okay? Now see that variable separation form, we take similar term together, okay? That means differentiation of a similar term, it comes together. So take a similar term. Now first of all, we can see y square similar, it is cancelled. So if we take y square, it goes to the numerator, it cancelled with this one, okay? So now see that dx x square it is denominator, take here, so we write x square dx, okay, and dz by z square it remain here, okay, dz by z square. How I have solved this one? Y square got cancelled, okay, x square denominator I taken here, x square dx, okay. So 1 upon z square, instead of finding the integration of 1 upon z square, take z square to the numerator, okay. So we write x square dx, which is equal to z raised to minus 2 dz, okay. Yes, now see that x square dx I kept it here, okay, z raised to minus 2 dz it is here, okay. Yes, so in order to remove dx and dz, so we have to apply the integration, okay. So integration of x square dx, which is equal to integration of z raised to minus 2 dz, okay. So x raised to 2 integration, what is the x square integration? X raised to n plus 1 upon n plus 1, that means x raised to 2 plus 1 upon 2 plus 1, that means we write x cube by 3, okay, x cube by 3 integration of x square, okay. Z raised to minus 2 integration z raised to minus 2 with respect to dz, then z raised to minus 2 plus 1 upon minus 2 plus 1, so we write z raised to minus 2 plus 1, that means z raised to minus 1 upon minus 1 plus c here, okay. Yes, so this one is our the integration of z raised to minus 2 here, okay. Yes, so we want the another constant. Now already we have one of the c1 here, you consider this one as a c2, okay. So I consider next constant as a c2 here, okay. Yes, so x cube by 3 keep as it is, okay. This term take it to the other side. Now see what we will get here, x cube by 3, okay, and which is equal to z raised to minus 1, take it to the denominator, and minus take it to the numerator, minus 1 upon z plus c2, okay, minus 1 by z plus c2 here. Yes, now what we do, we take that 3 to the other side, so x cube, which is equal to minus 3 by z plus 3 times c2, okay, minus 3 by z plus 3 times c2, okay, take that minus 3 by z here, so x cube plus 3 by, we write x cube plus 3 by z, which is equal to 3 times c2, okay. 3 is a constant, c2 is a constant, in differentiation both behave same, so I'm going to write it is the c2 only, okay. This one is a c2, which is equal to f2 of x, y, z, okay. This one is our required second solution, this one is our required first solution, okay. Now see that how easy the solution it is, okay. I hope you all have understood my entire solution. Nothing we have here, okay, everything it is easy, okay. I hope you all have understood everything, entire solution, okay. Don't have anything difficult, just need to understand first of all the symmetrical simultaneous differential equation, its entire process. After that, this one is the example I solved using the variable separation form. I explained you all here what is mean by variable separation form, okay. So variable separation means we take similar variable with the similar term of differentiation, and then we go for solving the further part, okay. Yes, that's it for our today's lecture, okay. So remaining example I will solve it in my next lecture, okay. So I hope you all have understood my entire today's session. So even after if you found anything difficult guys, let me know in my comment section, or if you have doubt in my today's lecture, let me know also, okay. So thank you everyone, thank you for my today's lecture.